When we're looking at an ideal gas, we're making some assumptions, and those assumptions are explained through kinetic theory. With kinetic theory, we're looking at a gas that is contained within a volume. So let's think about this in terms of a giant big square, just for the moment. I've got a large square, very large space. So our first thing is that we have gas inside of our volume, but the gas is very, very small in comparison to it. So if this was going to be my volume, I'm talking about tiny little dots that are going to be very far apart from each other in comparison to the size of the space. Our next assumption is that the gas is going to be moving. It can move in any direction it likes with any velocity it likes. Now, obviously, when we're talking about the velocity of it, the average velocity of those particles needs to obey our internal energy formula. So it's going to be the average kinetic energy is going to be equal to our 3 on 2 times by Boltzmann's constant times by the temperature. But each and every air particle will be spread out according to a Boltzmann distribution. Now, we won't go very much into the Boltzmann distribution, but if I gave you a quick graph, if our temperature of our room is here, it means that most particles are going to be existing with an average or average velocity, average kinetic energy around that temperature. But realistically, they could be traveling at any other speed. The next assumption is that all of our particles are having elastic collisions with themselves as well as the container walls. This is probably the most reasonable assumption where an elastic collision is actually going to be taking place, but certainly it is an assumption that is. Elastic collision means what? So it's kinetic energy, mainly because we're talking about a gas in this situation, so it will have some other potential energies, but the movement that it has, its kinetic energy and its potential energy is going to be conserved as part of that collision. It's not going to be transferred into a non-conservative force. It's not going to be transformed into heat. It's not going to be turned into sound in any way. Meaning that our kinetic energy initial plus our potential energy initial is going to be just being equal to our kinetic energy final plus our potential energy final. There's no other energy transfers going on in there. The next one is that Newton's laws hold true. And it is an assumption that we are making in this regard. Realistically, for gases in general, once you get into quantum theory and the idea of probabilities and how molecules actually move, as well as their interactions with electrons and other things, there's some more complicated stuff going on. But for an ideal gas, Newton's laws hold true. The final thing we can talk about is the idea that the gas does not interact with each other at a long distance, and only on a short distance we are having our collisions in that regard. So there are no large intermolecular forces that are affecting them as they are a larger distance away from each other. Once they get closer, there is very, very minor intermolecular forces. So those are our assumptions regarding what makes up an ideal gas. Primarily, Newton's laws hold true. There are no forces interacting between gas molecules, and that we have very small particles that have perfectly elastic collisions with themselves as well as the walls of the container.